Bismillahirrahmanirrahim. Okay, today I'm going to explain about chapter error correction and control. Okay, so in this chapter we are going to discuss how an error can be detected, and once the error is detected, then it can be corrected. Okay, so in this chapter I'm going to give a brief introduction about the error correction and control. Then I'm going to explain about type of errors and then how we can detect error and what are the mechanism or techniques for error correction. Okay, so network error control and error correction and control. Okay, so why we need to learn about this topic? The reason is that network must be able to transfer data from one device to another with acceptable accuracy. Okay, so it depending on what type of message that we are going to transmit. A system must guarantee that the data received are identical to the data transmitted. Anytime data are transmitted from one node to the next, they can become corrupted in passage. Okay, so it can be corrupted. It can be corrupted by the factor from the environment. Many factors can alter one or more bits of a message because the message is transmitted in the form of signal. So the signal represent bit 0 and 1. Okay, and because of the surrounding factor, it will affect to the bit and the signal itself, where the signal might change its shape. That implies that it change the bit as well. Some application require a mechanism for detecting and correcting error. Okay, some application can tolerate a small level of error. Okay, for example, random errors in audio or video transmission may be tolerable. Okay, so in audio and video transmission, the number of bit transmitted contain huge. The transmitted audio or video contain huge what you call it huge data. Okay, so it can tolerate with small level of error, but when we transfer text, we expect a very high level of accuracy. For example, if you are sending the word hello, for example, so at the receiver side, the receiver should receive the exact word hello. Okay, so at the data link layer, if a frame is corrupted between two nodes, it needs to be corrected before it continues its journey to the others. So need to be corrected first. Okay. However, most link layer protocol simply discard the frame and let the upper layer protocol handle the retransmission of the frame. This is what we have discussed in data link layer. Okay, when the receiver receive the frame which the unexpected one, so what will be done by what action will be taken by the receiver? It just discard the frame and request for the correct one. Ask for retransmission. Some multimedia application, however, try to correct the corrupted frame. Okay, some of the application won't do the same same as before, means that ask for retransmission but try to correct the corrupted frame. Okay, type of error. Okay, whenever bit flow from one point to another, they are subject to unpredictable changes because of interference. Okay, so we have learned about effective communication. We call it transmission impairment. So we have attenuation, distortion, and noise. Okay, all of this kind and all this kind of things might change the shape of the signal. Okay, so if one bit of a given data unit is changed from 1 to 0 or from 0 to 1, this is called as a single bit error. One bit affected, so this we call it as single bit error. If two or more bits have changed from 1 to 0 or from 0 to 1, this is called as burst error. So you can differentiate. We have single bit error. Okay, only one bit affected, either from 0 to 1 or 1 to 0. Okay, and we have burst error. Okay, burst error more than one or two or more bit have been changed to from 1 to 0 or 0 to 1. So type of error can be divided into two. One is single error, one bit. Okay, if two or more bit, this we call it as burst error. Okay, burst error is more likely to occur. So this is quite it's likely to be occurred. So it's a burst error and then single bit error, because the duration of noise signal is normally longer than the duration of a bit. Okay, so the reason why burst error is more likely to be occurred because of the duration of a noise signal normally longer than 1 bit. If the duration of noise signal is equal to the duration of 1 bit, then this we call as a single bit error, and that will produce single bit error. But if the duration of the noise signal is longer than duration of 1 bit, then more bit will be affected. So this is this will produce a burst error. Okay, so look at this example. If we are sending 1 kilobit per second, okay, a noise of 1 over 100 second. So how to calculate this? 1 over 100 multiplied by 1000. So cut this one and cut this one. So the answer is 10 bit. Okay, so if you are sending 1 megabit per second, so it's the same, 1 over 100 multiplied by 1 million. So the answer is 10,000 bits. Redundancy. Okay, so the central concept in detecting or correcting error is called redundancy. So we use redundancy concept for error detection and correction. To be able to detect or correct error, we need to send some extra bits. So in the concept of redundancy, we introduce some extra bit. We introduce some extra bit. We add this extra bit to our data. These redundant bits are added by the sender and removed by the receiver. So this redundant bit is just for error detection and correction. So their present allow the receiver to detect and correct corrupted bits. Detection versus correction. Which one is easier? Is it detection or correction? So the answer must be detection. Because correction is a bit difficult. The correction of error is more difficult than detection. In error detection, and the answer is only yes or no. If the data contain error, we just say that yes, it has an error. So we are looking to see if any error has occurred. So the answer is yes or no. And a single bit error, a single bit error is the same for us as a burst error, because we just want to know either the data or the message contain error or not. So the answer is just yes or no. But in error correction, we need to know the exact number of bit. How many bit that has been corrupted. And more importantly, their location. So this is number one, the exact number of corrupted bit. This is the second one, the location of the error. Okay, so the number of error and the size of the message are important, because we need to know when the size of the message is large, then so many possible location of the error need to be considered. So here, and look at this example. If we need to correct a single error in 8 data unit, 8-bit data unit. Let's say you have 1, 2, 3, 4, 5, 6, 7, 8. 8 data unit. So one bit has been corrupted. So either here, or here, or here, or here. So what is the possible location? So the possible location is 8 possible error location. And this is for one bit or a single error. Okay. So if we need to correct 2 error, let's say the error might be happen here at location 1 and 2. Okay, or 1 and 3, 1 and 4. So we don't know. So we can create a possible location. We can identify the possible location of the error. Okay, so how to calculate the total? So in total, actually, we need to consider 28 possibilities. Okay, how to calculate this? You use 8 combination of, it's not permutation, it's not permutation, this is wrong, combination 2. So the answer is 28. So you can imagine the receiver difficulty in finding 10 error in a data unit of 1000 bit. So how many possible error location need to be considered by the receiver? So it's hard today to do error correction, to correct the error, but it is easy to detect the error. Okay, so there are two main methods of error correction. One is forward error correction. This is the method of error correction. This is the number one, forward error correction. The second one is correction by retransmission. So what is forward error correction? Is is a process in which the receiver try to guess. Receiver try to guess the message by using redundant bit. This is possible, okay, if the number of error is small. Okay, correction by retransmission. This is much easier because once the receiver believe that the message contain error, so the receiver will discard the message of the frame and ask for retransmission. So correction by retransmission is a technique in which the receiver detect the occurrence of error and ask the sender to resend the message. And resending is repeated until a message arrives at the receiver where the receiver believe, this still on believe, is error free. So it is not certain. It is just the belief of the receiver. If the receiver believe that it has error free, it is error free, then it will accept it. Otherwise, it will ask for retransmission. Okay, next is coding. Redundancy is achieved through various coding scheme. The sender add redundant bit through a process that create a relationship between the redundant bit and the actual data bit. The receiver check the relationship between the two set of bit to detect error. The ratio of redundant bit to the data bit and the robustness of the process are important factor in any coding scheme. Okay, so in this chapter we are going to discuss about block coding. Okay, what is block coding? In block coding, we divide our message into block, of k bit, where it called as data word. We add r redundant bit to each block to make the length as n equal to k plus r. The resulting n bit block are called code word. N is called code word. R redundant bit, k data word. How the extra r bit are chosen or calculated is something we will discuss later. For the moment, it is important to know that we have a set of data word. This data word. Each of the size k and the set of code word. This is the code word size of n. So with k bit, we can create a combination of 2 to the power of, and it's not 2k, 2 to the power of k, small k up here. Okay, so let's say you have k equal to 2, so 2 to the power of k equal to 4. If k equal to 2, then the combination we have 4. The combination we have is that we can have 4 because 2 to the power of k. With the sign of with n bit, 2 to the power of n, and this is data word. So if k equal to 2, you can have 4 data word. If n equal to, let's say n equal to 3. So how many code word that you can have? 2 to the power of 3 is 8 in total. 8 data word. 8 code word. This is data word. This is code word. And for different value of n and k. Okay, since n always greater than k, this n is greater than k. Here n equal to 3, k equal to 2. The number of possible code word is larger than the number of possible data word. Yes, this is 8, this is 4. The block coding process is 1-to-1. Means that one data word mapped to one code word. And this is data word, this is code word. Okay, this means that we have 2n minus 2k. 2 to the power of k means that we have 8 minus 4 code word that are not used. So 8 minus 4 equal to 4. 4 code word not in use. So we call this code word invalid or illegal. So in this example, we have 4 valid code word, 4 invalid code word. The trick in error detection is the existence of this invalid code word. So we use this invalid code word to identify whether the message contain error or not. Okay, and this is an example. So k equal to 4, n equal to 5. So we have 2 to the power of k, 16 to the power of 4, 2 to the power of 5, 32 words. So if you subtract 32 minus 16, the answer is 16. So 16 code word, 16 code word are used for message transfer, and 16 code word for other purpose or unused, or to determine the invalid, or called as invalid code word, used to detect error. Error detection. How can error be detected by using block coding? If the following 2 conditions are met, the receiver can detect a change in the original code word. So what are the conditions? The first is the receiver has a list of valid code word. So the receiver must has this valid code word. If the original code word, if the received code word is invalid one, then the receiver could detect the error. It means that the receiver will identify that the message has been corrupted. Okay, so this is the process. First, data word, okay, combine with the generator and generate the redundant bit, add and produce code word. Okay, transmit over the unreliable transmission. So something might happen at the middle of the transmission process, and then at the receiver side, the receiver receive code word, and then the receiver check. If the received code word is in the valid code word, so it will be accepted and extract to get the data word. If the code word is not in the valid code word, so it will be discarded. Okay, and that is the process. Okay, example. Let's assume that k equal to 2 and equal to 3. Table 10.1 show the list of data word. So we have 2 to the power of 2 equal to 4 data word. So 0, 0, 0, 1, 1, 0, 1, 1. So these are the combination of 2 bit. Okay, and then this is the code word. So 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0. Okay, so this is the list of code word at the receiver side. So the receiver must has this code word for comparison with the received code word. Okay, so we need to consider different cases. Assume that the sender encode 01, this one 01 as 011 and send it to the receiver. Okay, so the receiver must has this table. Okay, when the receiver receive 011, so it will check with the list, this list. So 011 is in the list. Okay, so it will be considered as a valid code word. The receiver accept, extract and get the data word 01. So this is the original message that should be received by the receiver. The second situation, the code word is corrupted during the transmission. Okay, 011 has changed to 111. The first bit has changed from 0 to 1. So this is called as single bit error, isn't it? It's received. Okay. So when the receiver receives 111, the receiver will check with the table, the code word table. So 111 is not in the list. So what action will be taken by the receiver when the received code word is not in the list? So the code word will be discarded by the receiver. Okay. That is the second case. The third case, the code word is corrupted during transmission. Okay, 2 bit 11 over here has changed to 00. Okay, so when the receiver receives 000, it will check to the table. 000 is in the list. Okay, so what action will be taken by the receiver? The receiver will accept the incorrect code word, will accept the wrong code word, because why? Because the code word is in the list. So the receiver incorrectly extract the data word, and because once it accepts the code word, it will extract to get the data word, the original message. So the receiver has incorrectly extract the wrong data word, and because two corrupted bits have made the error undetectable. Error correction. Error correction is more difficult, as I mentioned before, than error detection. Okay, error detection, the receiver need to know only the received code word is invalid. In error correction, the receiver need to find or guess the original code word sent. We need more redundant bit for error correction than for error detection. Okay. So here we have a checker at the receiver side to identify the received code word is valid or invalid. Okay, this is another example. Let's add more redundant bit to the previous example, and now from 2 to 5. K equal to 2, n equal to 5. Okay, so we so we consider different cases. Assume that data word is 01. Okay, similar this one. Use the previous example. The sender consult the table or use to create the code word. So we have a bit longer code word with 3 redundant bits. The code word is corrupted during transmission, and this is supposed to be received by the receiver, and this one. But something has happened at the middle of the transmission process, and one bit, and the fourth bit has changed from 1 to 0. Okay, so what will be action? What action will be taken by the receiver? First, the receiver find that the received code word is not in the table. 01001 is not on the list. This means that error has occurred. The receiver assumes that there is only one bit corrupted, so uses the following strategy to guess the correct data word. So we have some strategy, some technique for error correction. So first thing first is the receiver need to identify either the message has contained error or not. So that is error detection. It must come first. Once the error been detected, it need to be corrected. So to correct the error, so the receiver need to know where is the location of the error. Okay, so that will bring us to the next step, the strategy of error correction. Okay, so for error correction, we have some concept, some technique we use Hamming distance, okay, and so on, and parity check bit, and so on. Okay, so what is Hamming distance? It is a central concept in coding for error control. Okay, Hamming distance between two words of the same size is the number of differences between the corresponding bit. Okay, so it's quite easy to identify the Hamming distance. Just look at this example. So if you can identify the difference. This is similar. The first bit is similar. Second bit is different. So 1. Third bit is different. 2. Fourth bit is similar. The fifth bit is different. So 3 differences. So the answer is 3. Okay, or you can use XOR operation. So you XOR 2 words. Okay. Count the number of mod in the result. Okay, so it will be equal. Either you identify the difference, or you use XOR operation and you count a number of 1 in the result, and to identify the Hamming distance. Okay, so this example, we have 2 examples over here. So the different bit between these 2 words is 2. Or you can use XOR operation. The answer is 0, 1, 1. Then you count bit 1. There are 2 bit 1, so the answer is 2. Okay, the answer is 2. Okay, if you compare these 2 words, 1, 2, 3 differences, so the answer is 3. Or you use XOR operation, you got 3 ones. So the answer is 3. The distance must be equal or greater than 0. So you can. So this is the number 2, 3, and now minimum Hamming distance for error detection. So minimum Hamming distance is the smallest Hamming distance between all possible pair of code words. So it's quite easy to determine minimum Hamming distance by using example. So you have a set of pair, a set of pair word. So you have this, and the answer is 2. Okay, until here 2. So the minimum Hamming distance for this all pairs is 2. Okay, so this is quite this is varies. So some got 3, some got 4. So the minimum is 3. Linear block code. Almost all block code used today belong to a subset of block code called linear block code. So here it use OR operation or addition modulo 2. It's quite easy for this one. For example, if you have 1, 1, 1. So how to get the answer of modulo 2? So 1 plus 1 plus 1 equal to 3 mod 2. So the remainder is 1. So this is even number. This is odd number. Odd number. Okay. So minimum distance for linear block code. Use minimum Hamming distance. Okay, parity check code. Okay. Perhaps the most familiar error detecting code is parity check code. Okay. So I will explain this by using an example. Okay, it's quite easy to determine the parity check code. Look at the first example. You have 0, 0, 0. So you add this number. If the answer is even number, then you need to add 0 at the last bit, at the most right bit. The most right. The far is over here. So add 0. Okay. So the second example, when you add them together, 0 plus 0 plus 0 plus 1, the answer is 1. 1 is odd number. So if odd number, then you need to add 1, bit 1. So easy. If the total is even, so you add bit 0. If the total is odd, then you add bit 1. That's it. Let's look at this example. So add them together. 1 plus 1 plus 1 plus 0 is 3. 3 is odd number. Is odd number. So add bit 1. So this is the parity check bit. Okay. Figure 10.0. The 10.4 shows a possible structure of encoder at the sender and at the decoder at the receiver side. So if you are this is at the sender side, you have a data word. Okay, so you add them together. If the answer is even, and then add 0 bit. Generator will produce the parity bit. Call it a parity bit. If the total number here, let's say 1 plus 1 plus 1 plus 0 equal to 3, odd number. So the generator will generate parity bit 1. Okay, so and it will be transmitted, it will be combined and transmitted. So at the receiver side, the received code word will be forward to the checker. So it will check either, let's say if you transmit 1110, so you will be added with the parity bit, and the generator will generate parity bit, so it become 11101. Okay, so the receiver receive 11101. Okay, so this code word will be sent to the checker. So the checker will check either this parity bit is correct or wrong. So let's say if something has happened at the middle of the transmission process and one bit over here has changed. Let's say 1101. So what will be happen at the checker? The checker will add this number, find the total. Now the number is, it should be odd, because 1 plus 1 plus 1 plus 0 is 3. 3 is odd. So when it is odd, so it will check the parity bit. Is it 1? If 1, then it will accept it. Okay, so but if we look at this case, let's say bit 3 has changed from 1 to 0. So when the checker check this one, add them together, 1100. So the answer is 2. 2 is even, and the parity must be 0. But now is 1. So the checker will identify that something has happened to the message or to the data, and because the number, the parity bit is not supposed to be like this, so it will be discarded. Okay, it will be discarded. If the receiver receive this one, it will be accept it. Accept. Okay, so that's all for this chapter. Okay, I hope that you enjoy by listening to my lecture today. And yes, that's all for now. Thank you very much. Assalamualaikum and have a nice day.